Hello everyone. I'm Dr. J. John C., Assistant Professor, Department of Mathematics, Fatima College. In this lecture, we are going to explore the fascinating world of maximum likelihood estimation. This is the fundamental concept in statistical inference that helps us understand how to estimate the parameters in a model. Let's get started. In this course, we initiate on a four-part learning journey. We begin with the fundamentals of likelihood to establish our core principles. Next, we examine the regularity conditions that ensure our inferences are valid. Once grounded, we explore theoretical bounds to understand how our estimators behave in the long run. Finally, we conclude by applying these techniques to hypothesis testing. Welcome to section 1, where we build the foundation for maximum likelihood estimation. We focus on three critical pillars: understanding likelihood functions, mastering log likelihood transformations, and defining the maximum likelihood estimations itself. By learning the translate observed data into parameter estimates, you gain a powerful tool for statistical modeling. These core principles are not just theoretical, they are the essential building blocks that allow us to drive robust, reliable conclusions from complex data sets later in the course. Think of the sample space simply as a complete catalog of everything that could possibly happen. Whether you are flipping a coin, rolling a die, or measuring a continuous value, the sample space is just the collection of all those potential outcomes. It sets the stage for our analysis. By defining the entire universe of possibilities we might encounter, allowing us to build a precise mathematical foundation for our mathematical models. Think of likelihood function as a way to measure the um, uh, different models. Once we have collected our data, we ask ourselves, for a given parameter value, how likely would it be to see this specific data? It isn't a probability of the parameters themselves, but rather a, a collection of how well our model explains what we actually observed. The peak of this function shows as which parameter value best fits our evidence. In practice, we rarely work with the likelihood function directly. Instead, we use the log likelihood. Why? Because multiplying many tiny probabilities together often leads to numbers so small that computers struggle to handle them accurately. By applying a natural logarithm, we transform complex multiplication into simple addition. This makes our calculations much easier to manage, prevents numerical errors, and significantly simplifies the calculus required to find the parameter values that best fit our observed data. The maximum likelihood estimator is essentially a strategy for making an educated guess about our data. We are looking for the specific parameter value that makes our observed data most likely to occur. Think of it as tuning a dial until the model best fits what we have actually seen. By finding this best fit value, we maximize the probability that our theoretical model matches our real world observations. So in the first, it is the definition of the mathematical likelihood estimation. It is denoted by theta cap. It is the arg max of the likelihood function. It is the maximum of the likelihood function. These are all the steps how to find the maximum likelihood estimator. To find the maximum likelihood estimator, first to take the first derivative of the log likelihood function and set it equal to 0, solve for theta to find the critical points, verify its maximum, check the second derivative of the log likelihood function is less than 0. And why log likelihood function? We work with log likelihood because maximizing the log likelihood function gives the same result as maximizing the likelihood function. Differentiation is much simpler with the sums than products. So numerical stability is improved when we are using logarithm. Next, let's apply the maximum likelihood estimator to the Bernoulli distribution. This model is perfect for simple yes or no experiments like flipping a coin or measuring a binary outcome. Our goal here is to find the best possible estimate for the probability of success, theta based on our observed data. By walking through the likelihood function and its derivative, we arrive at a very intuitive result. The maximum likelihood estimation is simply the sample mean. So the given consider the sequence of Bernoulli trials. The probability mass function has been given, that is P of x is equal to theta power x 1 minus theta whole power 1 minus x. X takes 0 comma 1. N independent observations. The question is find the maximum likelihood estimator of theta. So first we should find the likelihood function. So we know that the likelihood function is the product of the all n variable, product of the all probability mass functions for n variables. And next we'll take the log likelihood function, so which is nothing but the product has been transformed into summation. Next, we should find the derivative, first derivative, and equate it to 0. Then we'll get the critical point. Then here, maximum likelihood theta cap is equal to x bar. It is a sample mean. Now let's examine the Poisson distribution, which is essential for modeling the number of events occurring in a fixed interval, such as customer arrivals at a store or incoming phone calls. By applying the maximum likelihood estimation method here, we can effectively determine the average rate of these occurrences. As we work through the log likelihood and derivative, we find that once again our best estimate for theta is simply the sample mean of our data. So for this Poisson distribution, the probability mass function is given, that is e power minus theta, theta power x by x factorial, x belongs to 0, 1 to 3, etc. up to and given n variable, n independent observations and find the maximum likelihood function, maximum likelihood estimator of theta is the question. Then the steps are likelihood function. Then the next to take log likelihood function. Then take the derivative and which is equated to 0. This is also the maximum likelihood estimator of theta is also same like binomial. It is also sample mean. Now let's explore the normal distribution. In this case, we are estimating the unknown mean when the variance is already fixed. This scenario is incredibly common in real world data analysis, such as measuring manufacturing precision, where the machine's spread is consistent. As we drive the maximum likelihood estimator, we find that the sample mean remains our best estimate for the population center, confirming that even with the known variance, the simple average is our most powerful tool. So for the normal distribution, it is the probability density function is given. Then the question is find the maximum likelihood estimator of theta. So all the 4 steps, the MLE, that is maximum likelihood estimation of the mean is sample mean x bar, regardless of the known variance x sigma square. The invariant property is a major time saver in statistics. In simple terms, it means that if you have already found the best estimate for a specific parameter, we do not need to start over to estimate a function of the parameter. We can simply apply the same function to our original estimate. This allows us to easily calculate complex values like probabilities or rates directly from our existing findings. Next, properties of maximum likelihood estimators. The first one is consistency. Consistency is the idea of maximum likelihood estimation. This means our calculated value will eventually settle on the true population parameter as our sample size grows infinitely large. It's foundational property because it gives us confidence that our methods are reliable. Essentially, the more evidence we gather, the closer we get to the truth, making MLE, that is maximum likelihood estimator, a highly robust choice for a data analysis. Asymptotic normality property. Asymptotic normality is a powerful concept in statistics. It tells us that with large sample sizes, the distribution of our maximum likelihood estimate will follow a bell curve centered around the true parameter value. This predictable shape allows us to perform hypothesis tests and calculate confidence intervals with precision. Essentially, as we gather more data, our estimates become not only more accurate but also more stable, providing a reliable mathematical foundation for making predictions and inferences. Summary. In this section, we established the fundamental pillars of maximum likelihood estimation. We began by defining the likelihood function to measure parameter reliability. Then moved to the log likelihood to simplify optimization through summation. Finally, we defined the maximum likelihood estimator as the value that maximizes this function. These core concepts provide the mathematical foundation for everything that follows, allowing us to derive estimators, assess their properties, and confidently apply these methods to various statistical distributions and real world data problems. Conclusion. Thank you for your attention throughout this first section. By establishing these fundamental pillars of maximum likelihood estimation, we are now well prepared for what lies ahead. In our next section, we will dive deeper into the mathematical conditions required for these methods to work properly, ensuring we can apply them with both accuracy and confidence. Thank you.